Hello everyone, I'm Norman Wahlberger and we're talking about the sociology of pure mathematics and in particular number systems. And I'm trying to sort of expand your potential thinking in this direction by going back historically, looking at the Egyptians, the Babylonians, and now I've introduced this newfangled centimole kind of arithmetic. It's a variant of our Hindu-Arabic system, which however parallels more closely the way the Babylonians thought about arithmetic. So it's our chance to practice thinking like Babylonians. And today we're going to tackle the most difficult of the four fundamental operations: addition, multiplication, subtraction, and the most difficult one is always division. It's almost the heart of the matter, even from earliest times to even modern computational systems. Still, division is much more problematic, expensive, etc. than the other operations. So let's have a look at some of the issues here. So suppose that we just ask a primary school student, what's 24 divided by 6? Well, the answer is 4. And how do they know that? Well, they can look it up on a multiplication table. So they know that 4 times 6 is 24, so that means that 24 divided by 6 is going to be 4. So that's a sort of reversing of what's on a multiplication table. A little bit more sophisticated, 24 divided by 5. So that's not on a multiplication table. Something else has to be done to appreciate that. The answer is 4.8. That's a decimal number, and that's typically done by using something called long division, which you may or may not have learned as a student. In my day, yes, we had to learn long division, but I think perhaps students these days don't spend so much time on that. Okay, here is a very different kind of problem. It looks very much the same. What's 24 divided by 7? Well, if you perform this long division, okay, and it is a little bit of an elaborate process, but you start performing this long division, you see that it doesn't seem to end. It sort of keeps on going. Okay, it doesn't finish like this one did. So you end up with 3.42885, and you're keeping on doing this process, 5, and then that's 7, and then 1, and then 4, then 2, and then 8, and then 5, and then 7, and then 1, and then 4, and 2. Okay, so maybe you get up to this stage here, and then you look at it and say, well, actually, wait a minute, there's a kind of a pattern here. We're getting this 4, 2, 8, 5, 7, 1, and then it repeats, 4, 2, 8, 5, 7, 1. It's a repeating kind of decimal. So it doesn't end. Okay, we're going outside this realm of finite decimal arithmetic and sort of invoking these new kinds of objects called repeated decimals. So we might be inclined to rewrite this, capturing that repeating thing by writing it as 3.428571 with a bar over it, say, to represent this repeating aspect. So this requires us to perform a long division and notice a pattern. Okay, that's not that onerous when the pattern only consists of half a dozen numbers. But if the pattern involves a half a billion numbers, then saying what does it mean to notice a pattern? How do you notice a pattern in general? That's actually, hugely challenging to understand. So this particular division is a lot more complicated than these two divisions, even though on the face of it, they look very parallel. So here is a more complicated example that shows us just the difficulties that we are likely encountering with this division operation. Suppose we take this number, 1, followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then a 1. And we're dividing it by this number, which is 26, I guess that's ones, thousands, millions, billions. So 26,798,700,427. Sort of in that base 1,000 way that we like to write in numbers. Okay, what is the result of this division? Well, again, you can get your computer perhaps, or you can do it longhand also. You get a long division process going. And it starts 3.731524230938036299874937. And at that point, maybe my computer stops. Although I know that the algorithm itself doesn't stop, just that I've run out of memory or time or energy or something. So we could extend this, but it's not at all clear what the pattern is. In fact, it's very likely that the repeating aspect of this answer is not evident for many miles, or at least for many, maybe millions of digits. This is here, what do we say, 26 billion. So when you think about long division, you realize that there's sort of 26 billion possible remainders. So in principle, you could cycle through a lot of those remainders before you got kind of a repetition. So in principle, this really could go on for a long time before you even are in a position to notice some kind of repeating pattern. So that's computationally basically almost impossible unless you have some supercomputer, I suppose, at your disposal. Now we have another number system floating around in the modern world that young people learn about, actually also in primary school. And that's the theory of fractions, or rational numbers, which you very likely hated when you were in school. And perhaps for some reasonable reason, actually, because arithmetic with fractions is fraught with difficulties. It's fraught with logical subtleties, okay, that can be surmounted, but to do so requires a fair amount of sophistication. And in fact, the practical applications of fractions, as I pointed out other places, is ultimately rather limited when you go past sort of kitchen, cooking, recipe kinds of applications. In science and in engineering and practical real-life applications, fractions are very quickly dispensed with, and we typically move to a decimal, or even approximate decimal kind of framework. Nevertheless, okay, one thing that we do learn as students is that fractions provide a kind of pleasant, in sort of theoretical environment in which division becomes dramatically simplified. One might almost say tautological, because the way we would rescue this seemingly impossible division is to say, well, that this number divided by this number is the fraction 1,000,000,001 over this number 2679870000427. That fraction is the answer that you get after you've performed this operation. Now, a Babylonian scribe would look at this and say, well, that's hilarious. That's hilarious. Are you serious? This is the way you're going to do arithmetic. You're basically just going to repeat the question in a slightly different form and say, oh, now we have an answer. It's not really so much different from the way my analyst friends do real number arithmetic, I remind you, where you have a question like, what's cosine of 5 plus log 7? And the answer is, oh, it's cosine 5 plus log 7. That's the way we do real number arithmetic. There's some parallels here. So this is clearly unsatisfactory from a Babylonian point of view. A Babylonian scribe would say, well, you haven't actually performed the division. That's still waiting to be done. This is just a placeholder for an operation which you have not yet performed. So we might say, okay, yeah, our Babylonian scribe friend has a point. Maybe we'll stick with repeating decimals. We'll say that the results of divisions are repeating decimals. So for that, we need an arithmetic of repeating decimals, which surely is not that much more onerous than just our regular theory of arithmetic with regular decimal numbers. Well, unfortunately, ladies and gentlemen, the situation is somewhat more delicate than that. In fact, I claim that a logical treatment of operations with so-called repeating decimals is pretty well missing in modern pure mathematics. We don't have proper definitions of these operations at the level of repeating decimals, and we don't have proofs of the laws of arithmetic that we would want for those operations dealing with repeating decimals. So what I'm saying here is that if we're working in the world of repeating decimals, like these kinds of things, okay, there's x, which is 3.42857, that's repeated, let's say, and y is 2104, and then the 319 is repeated. Okay, the question is, what are actually the algorithms for computing these various operations, say on two typical repeating decimals? So what's the algorithm for obtaining x plus y? So x plus y should be another repeating decimal, okay? So it's just a finite thing, so you should be able to write it down. You've got finite input here ultimately, and there's going to be a finite output. So how do you get that finite output from the finite inputs? And you can repeat that question for each of the four operations. And we're assuming that repeating decimals x and y are given. Well, there is in fact a way of doing this that in some sense is known to primary school students, because they know, or they're taught at some point, that repeating decimals are pretty well equivalent to fractions. Exactly because when you do the long division of a fraction, the way a Babylonian might want you to do, then you're going to get a repeating decimal. So what you can do is, there's a kind of a way of going backwards. So given a repeating decimal like this or like this, you could convert those back into fractions. And then you could do the operations at the level of the fractions and then convert back to a repeating decimal. Although admittedly that's kind of a cheating, right? Because that means you're going actually outside this numerical system that you're trying to establish and saying, okay, we're going to actually use some different arithmetic in order to substantiate this arithmetic that we want to create over here in the world of repeating decimals. In particular, if you're a real number enthusiast, and presumably you have a theory of real number or infinite decimal arithmetic, which includes repeating decimals just as special cases, then you should just be able to take that existing theory and simply specialize it to this very special and relatively simple case. Anyway, this is a very subtle question. I doubt if there's more than a handful of people who really know how to do this, and my guess is, in fact, that there's probably nobody who knows how to do it properly. So this is going to be a really interesting theme for us. Just how convoluted is the current landscape of number systems? And does it really work? To what extent does it really work? And to what extent are there all kinds of logical holes which are just more or less ignored, or we pretend that these are sort of elementary considerations which are beneath our consideration? So that's a very interesting sociological question, obviously, because arithmetic is, at the heart of mathematics education. And if there are really fundamental issues with the logical structure of this subject, then that has a lot to do with the education of young people, as well as more advanced applications theoretically. So I want to contrast our rather jumbled landscape of numerical systems with the Babylonian system, which was, I think, fair to say, much tighter and more logically consistent. But they paid a price for that, okay, which maybe to us at first seems like a weakness, but when we look more carefully, we see that this is just a result of them being more careful, more clear, more logical about the way we do things. Okay, so in order to try to explain this issue, I want to move to this sentinel point of view that I've introduced in my last video, which allows us to see the way the Babylonians thought in a more familiar way, because it's much closer to our base 10 system. So let me remind you that we have sentinel numbers, which are basically base 100 numbers, digits from 1 to 99. So here is a sentinel number, 2317. Here's another one, 4152. And I've explained that the product is going to be another sentinel number, in this case 962,184. And the question of the absolute values of these numbers, so where the decimal or centimale points are, is sort of irrelevant. There is no centimale point, okay? So these numbers are sort of floating freely. The actual centimale point or decimal point is sort of freely floating. When we talk about addition and subtraction, however, in order for things to be sort of clear, we need an alignment of things. So in this context here, we have these digits of this centimal number and these digits of this centimal number sort of aligned. The 43 on top of the 58, the 81 over the 92. When we align them like this, then addition becomes possible, and it's just like pretty well the usual addition. Although, we would probably better think about the way the Babylonians did it in terms of an abacus. But anyway, we can sort of understand it this way, and subtraction, the same kind of thing. So these are the three relatively simple operations. And now we come to division, which is the much more complicated operation. So how does that go? Well, the answer is, it's the same kind of answer that a Babylonian would have given, is that if you want to do division exactly, you have to limit yourself. You can't divide by any old number. Division exactly only works in the centimal world when you're dividing by a centimal regular number. What does that mean? That's a number which is a product of 2's and 5's. It's exactly those numbers that it turns out that we can divide exactly by. In the Babylonian world, base 60 has factors 2, 3, and 5. So almost the same, except that there's a crucial third number, the number 3, which is included in potential factors of regular numbers. And this makes a huge difference. It means that in the sexagesimal world, there are a lot more regular numbers than in the centimal or base 10 world, which means that their capacity of doing division is greatly increased over our capacity, whether we're working in base 10 or working in base 100. This is an interesting point to get your head around. The idea that, first of all, the number system that you're working in does matter, at least when it comes to division. And that if you're concerned with division and you want to have an effective kind of, or as effective as possible, well, then the Babylonian system is a step up above our systems, whether it's base 10 or base 100. And this is a disconcerting realization, but it's the way it is. So at the heart of the Babylonian approach to division was their reciprocal table, and we've already had a look at it. In the centimal world, there's also a reciprocal table, but it's simpler. It's more familiar, and it's also smaller than the base 60 system. So it's easier for us to get our heads around what's happening here. This is the reason, one of the reasons I'm trying to advocate this centimal point of view, because it brings into focus much more easily the role of the reciprocal table. So the centimal reciprocal table, base 100, here are numbers n, and here are their reciprocals, n bar. N bar, N bar, N bar. And we're going basically through the numbers from 2 to 99 or 100. And once we get to 100, it's basically 1. And going a little bit beyond, because that's also what happened in the Babylonian case. So it's basically a list of regular numbers, or at least small regular numbers, single-digit regular numbers, okay, where a digit means something between 1 and 99. So these are the numbers which are multiples of 2's and 5's from 1 up to 1. So the reciprocal of 2 is 50, because 2 times 50 is, well, we would say 100, but 100 is the same as 1 in their floating point system. 4 times 25 is 1. 5 times 20 is 1. 8 times 12, 50 is 1. So the reciprocal of 8 is 1250. Reciprocal of 10 is 10. Reciprocal of 16 is 625. Reciprocal of 20 is 5. Well, I guess that's just the same as this one, just reversed. The reciprocal of 25 is 4. It's really the same as that. The reciprocal of 32 is 31250. We get a number with 3 digits. Reciprocal of 40 is 250. The reciprocal of 50 is 20. Reciprocal of 64 is 15625. Reciprocal of 80 is 125. The reciprocal of 1 is 1. The reciprocal of 1.25 is 80. The reciprocal of 128 is 781250. So if we were Sentinel scribes, we would want to memorize this table. And in some sense, you're probably already familiar with aspects of this. You probably know that dividing by 8 is the same as multiplying by 0.125. Another example, 57 divided by 16. So we look for 16 in our reciprocal table. Look at the reciprocal, it's 625. So that's the same thing as 57 times 625. Okay, and there you have to do some multiplication, perhaps with an abacus, to get 356 25. Now, if we were going to convert this into our sort of fixed point floating system, so 57 divided by 16, it's going to be a little bit more than 3. So we would want to put our decimal point right there and interpret this as being 3.5625. So I want to stress to you that we can extract from these kinds of equations that are familiar to us in the Hindu-Arabic world. Right? So this one here is really saying 57 divided by 16 is equal to 3.5625. That's what makes this a little bit attractive, is that we can quickly appreciate what's going on, because 100 is not so different from 10 in terms of the base. So here's an example of a multiplication division table in the Sentinel framework. I'm just going to look at multiples of 3, 12, 50. Why 3, 12, 50? Well, if you look on our reciprocal table that I just showed you, 3, 12, 50 is the reciprocal of 32. So that's one of the entries. So following a Babylonian tradition, we should create a table of multiples of 3, 12, 50. So times 1 is 3, 12, 50, times 2 is 625, times 3 is 937, 5, and you can have a look down to 10. And then it makes sense to go with further multiples of 10. So times 20 is 6250, times 30 is 9375, times 40 is 125, times 50 is 15625, times 60, times 70, times 80, times 90 is 28125. So why would we want to have multiples of 3, 12, 50? Is it because this is a multiplication that's likely to pop up at us in applications? Not so much. It's more indirect than that. It's the division by 32 that we're more interested in. Okay? The division by 32 in this Babylonian setting translates to a multiplication by the reciprocal. Okay? So we end up wanting to multiply by 3, 12, 50. If we're, say, taking 67 divided by 32, that's the same as 67 times 3, 12, 50. And then we could use this table to pretty easily calculate that, because the 67 is like 60, 60 right here. Okay, so 60 times the reciprocal, 3, 12, 50, is 187.50. There it is right there. And 7 times the same thing, 7 is over here, 7 times the 3, 12, 50 is 2187.50. So now we have to add these two. But this is one of these cases where you have to add, but in order to add, you have to align them. Okay, you have to know which ones sort of go with which ones. And in this case, it's the 87 that goes with the 21. Okay, so put that over that, the 50 over the 87, and the 50 is sticking out. And then you do the addition, and you get 2, 9, 37, 5. No, you get 50, yes, sorry. I think there should be a 50 here. Okay, so 67 divided by 32 is 2, 9, 37, 50. If we were going to convert this into a Hindu-Arabic form, well, the decimal point would be right there, because 67 divided by 32 is going to be roughly 2. So it's going to be 2.09, 2.09, that's really an O line, 2.09375. But that 5 is really 50, okay? So in the Sentinel point of view, I need that 0 over there. So that's a single multiplication division table that's parallel to the kinds of things that the Babylonians had, that illustrates that division was an important usage for this kind of table. All right, so we might aspire to creating a Sentinel combined multiplication division table, which is parallel to what the old Babylonians had, where we basically combine all the various multiplication division tables. And so let's agree that multiples that we're going to be talking about are, say, multiples times 2, times 3, all the way up to 10, and then all them also multiples of 20, 30, 40, up to 90, because that's sort of the standard multiplication division table by itself. And then what we want to do is we want to list multiples of pretty well everything that's on the standard Sentinel reciprocal table, that table of reciprocals. And in the Babylonian times, there would have been some additional entries occasionally. So I'm going to just show you here briefly just some slides of what I've cooked up to be a combined multiplication division table in the Sentinel story. And so here you can see some various tables of various multiples of these various things. And overall, I would say that this is still going to be it's going to be comparable to a Babylonian combined multiplication table, but maybe somewhat. Okay, so let's just give another illustration. So suppose we have 57 divided by 16. How would we do that? Well, we would look this up. 16, the reciprocal of 16 is 625. Then we would write that 57 as 50 and 7. Look up the various multiples of 625 on the corresponding multiple division table. They are 3, 12, 50, and 43, 75. Combine them in the appropriate way. In this case, the 12 over the 43, the 50 over the 75, to get 356, 25. And I'd like to point out that J. Freiberg, who's a sort of world authority on Babylonian texts and has done all kinds of amazing work in this direction, in a great book in 2007 called A Remarkable Collection of Babylonian Mathematical Texts, he really does, I think, point out this direction that there's a reasonable chance that division was an important ingredient in the motivation for these tables, which have been priorly called multiplication tables. So this is not just our idea that they should be called division tables. So I hope this little insight into the complexities of division intrigues you. But there's another very important sort of numerical aspect that I want to talk about also in a Sentinel point of view. I want to shed a little bit of light on the way the old Babylonians thought about square roots, taking square roots. And I'm going to draw upon some of the insights of my colleague Daniel Mansfield for that and give you a sort of a Sentinel version of that very interesting story. I'm Norman Wahlberger. Thanks for listening.